So now we still need to construct a 4-vector for the force, which is valid in the flat spacetime of special relativity. First of all, we want to compare what we know about the force from Newtonian physics with what we know from the three-dimensional formulation of special relativity, together with the knowledge we gained from our 4-momentum vector. We will be able to construct the 4-force vector. So let's start. We call this 4-force also Minkowski Force. Okay, first let's compare Newtonian physics with special relativity in 3 dimensions. So Newton tells us that a force is equal, force acting upon a moving body is equal to its time derivative of its linear momentum. That means we can put differential operator in front of the brackets and use the known formula m times, so the mass times the velocity u of the particle. So in case now that the mass is constant, that means, for example, we don't consider exhaustion accelerating bodies like a rocket, then, so in case m is a constant, the mass is constant, it follows directly that F equals the known formula mass times acceleration. So now let's go over to the transformation law for the force. So as we know, special relativity is mainly dealing with problems of different inertial frames. We now want to know how the transformation laws apply to the force in Newtonian physics. We call those the Galilei transformation. To introduce these, we start with a little thought experiment. We have an inertial frame, let's call it S, and another inertial frame should be a train passing by with constant velocity v. This is the S primed inertial frame, and within this train there is a door, and this connects 2 apartments of the train, and so a passenger of the train wants to open this door and he has to apply the force F prime. So what about the coordinates? First we want to deal with the coordinates. So we make 2 diagrams. The horizontal axis in direction x or x1, and so there is a moving. So the first is stationary. We look at stationary S, and S prime is moving with velocity v. So the transformation of the coordinates for an inertial experimentator in S, for S, so the transformation for S towards S prime, S primed, as the experimentator in S has only access to his measurements, which are the unprimed coordinates, he can calculate the prime x coordinate of a, let's say, of a point fixed to this train. If he uses his measured x value of this point and subtracts from this the traveled distance v times t. This means this is the measured x distance of the experimentator in S. So what about the force now? Is a force somehow changed by this transformation? So we want to verify that if a train is at rest, the force you will have to apply is the same as it if it's moving with constant velocity. So how do we do that with means of physics? So we apply the law of force, which Newton tells us it is F equals m times second time derivative of the x coordinate. And here we just insert what we know from our Galilean transformation. That means that x equals x primed plus vt. Okay, so we get m, the mass, times the second time derivative of x prime plus vt. And the second time derivative of the expression v times t is 0, as v is a constant. So we just get m times x double dot primed. This equals f dash. So as we know, f equals f primed. This means that the door, so you can open the door with the same force whether you are moving with constant velocity or you are at rest. Now let's go over and repeat. So I want to emphasize it's just a repetition of what we know from special relativity. So I won't go into details, but yeah, just summarize. So special relativity tells us that a force, so just a second. Okay, I will call it now as well F. So F equals, it tells us F equals relativistic linear momentum, the time derivative of the relativistic linear three-dimensional momentum. Okay, and this equals the time derivative of relativistic momentum equals the Lorentz factor, so gamma u. It's a Lorentz factor of a moving particle with velocity u times the rest mass m0 times velocity u. So, and here we have to take into account that gamma u is a function of the time, can be a function of the time in case that u is also a function of the time. So let's just go a little bit into details. As we know, gamma u equals 1 over the square root of 1 minus u, I call it now u of t squared over c squared. So it's obvious that gamma u, we need to exert a time derivative on gamma u and also on u, so on the velocity u. And therefore it follows, so I just give this as an insertion here, it follows that this time derivative we have to use the product rule of differentiation. So we get gamma u times m0 times the acceleration. So I give all the three-dimensional Newtonian the Newtonian vectors where needed an index with a little 3 in brackets. Okay, plus gamma u to the power of 3 times u 3 times a3 over c squared m0 times u3. From the 3D formulation of special relativity, we also found out that we need to be able to construct the correct laws of movement. We will need also an expression for the time derivative of the relativistic energy. This is equal to the relativistic power, and as we know, force times the velocity is equal to the power. So in relativity, it's equal to time derivative of relativistic energy, and we know that relativistic energy equals the relativistic moving mass times c squared. So we have here a gamma u times m0 times c squared. And from that, it follows an expression which we need for the Lorentz transformation. It's f3 times u, so 3 over c equals 1 over c dE by dt equal 1 over c d over dt of just the energy E, relativistic energy E. Okay, now let's go over to the Lorentz transformation for the force. So, completely different to the Galilean transformation, we will now have to exert a Lorentz transformation. So I call it just LT. LT, Lorentz transformation for S towards S dash for S primed. And we have seen that we need 4 expressions or 4 components which we will have to transform. And there is this one which connects force to the time derivative of energy, and this transforms according to the following rule: F times u 3 over c primed equals F3 times u3 c minus beta 1 F3 1. So for this transformation, we just take into account a standard, a configuration where the relative movement between S and S prime is in x direction. So this beta equals, just for exactness, beta 1 equals V1 over C. Okay, so we have here the denominator 1 minus V1 times U1 C squared. So please be aware, I just use the tensor index notation where first of all, I don't use x, y, and z for the coordinates, but x1, x2, and x3. And this index formulation I keep for all tensor expressions. It means for vectors and also for higher ranked tensors. Okay, so and for F1, so this is the force components acting in x1 direction. We get the transformation. So we have F1 prime equals f1, so that's also of f3 here, so this is f31 minus beta 1 over f3 times u3 over c squared, over c minus v1 u1 c squared. So and for f2 and f3 we get the same expression, divided by gamma v minus v1 u1 c squared. Okay, and here we directly see that f does not equal f primed. Okay, this is just a repetition and comparison what we know from Newtonian physics and special relativity about the force. Already we have constructed two different four vectors. It is the four momentum, the four linear momentum, and the four acceleration. And now for sure we want both to play a role for our four force. So let's see how does our four momentum vector look like. For momentum, just again a repetition. Our four momentum vector has following components. So P, or in index formulation, P mu equals E over C and P1, P2, P3. So just for exactness here, just give the standard, that it has four components, P1, 0, 1, 2, and P3. It's capital P here always, and those are the four components. So this means we can summarize it in the following way. The 0 or time component, E over C, and here we have just the relativistic momentum, the three-dimensional spatial relativistic momentum of a particle. Okay, and this is constructed such that it equals the rest mass m0 times the 4 velocity of a particle. Okay. So, and what do we know about the 4 acceleration? We have already derived this in the last video, and so let's repeat what is the Minkowski norm of this 4 momentum. Okay, just do it for completeness. Minkowski norm of this vector leads to the energy momentum relation the following way. So P mu times P mu equals E squared over C squared minus P squared. Okay, and this equals, as we know, it is, we go to the expression, the last expression after the equal sign. We have m0 squared times mu times mu, and yeah, this we already know it's equal to c squared, so we have m0 squared times c squared. Minkowski norm, in this case it's the energy, momentum energy relation. Okay, now we know for the 4 acceleration, so b mu equals, okay, so this was, we got this by the proper time derivative of for velocity. So maybe I just emphasize again, to construct those 4 vectors, we always need the concept of the rest frame of a moving particle and the proper time. The proper time is the time of the clock of a clock which is moving together with a particle. Okay, so we have proper time derivative of the for velocity, and here we have to apply the chain rule, so we would get time derivative, the derivative of by t, and there t over d tau, proper time. So, and this led us to, so now comes a longer calculation, but we get the following vector components: u to the power of 4, u3 times a3 over c for the first, so the timely component, and spatial components look like this. This is mainly due to the derivative of this gamma factor. We get such complicated expressions here. So for sure, I won't do it in detail now, but just for repetition. And so this is our 4 acceleration. And now from all this knowledge, we want to derive the 4 force. So there shouldn't be any contradiction to what we have done so far. So this would mean, first of all, what we need. So I put it here, needs the following. Following is what we want or what we need for our 4 force. We call this 4 force K. So first you want to have that K mu equals the proper time derivative of the 4 momentum. And on the other hand, we also want to have that K mu equals the rest mass times the 4 acceleration. This should hold true, and also all what we have done in our repetition of the 3-dimensional formulation of special relativity, so that the spatial component f equals the time derivative of the relativistic linear momentum. Okay. So we need 4 components. How can we continue here? If we look at the expression which we have gained from the relativistic power, which is the time derivative of the relativistic energy, and here we constructed F times U over C, we compare it and we will see the following. We need now a completely 4-dimensional description. Okay, so we look at our first component. This was F3 times U over C, so which is equal to 1 over C of the relativistic energy. So this was dt mu times C. Now we take a look at the 4 momentum. The first component of the 4 momentum equals E over C. And E over C for sure is exactly what we have here in brackets, m0 times gamma u times C. So this is equal to a time derivative of the 0 component of the 4 momentum. But we have to take care it's not the proper time derivative, but just the ordinary coordinate time of the lab frame S. Okay, now let's look at the other spatial components. So F3, 1 equals the time derivative, we know that. It's the time derivative of the first component of the 3-dimensional relativistic momentum. It's equal to m0 gamma u times u1. So in F, the other components 2 and 3 are analogous. So we can summarize this and we immediately see that we get F3 equals gamma u 0a plus, it's already what we have gotten for what we have got for the spatial spatial relativistic force. So now we can apply a trick to get the proper time into play. We just multiply both sides of the equations with the factor gamma u. So what does this lead to? We multiply both sides with gamma u. Why do we do that? It's because we know that this is equal to proper time derivative of lab frame time. This was our great advantage when we used the rest frame of a moving particle. So we multiply both sides with gamma u. Thus we bring, let's say we bring the rest frame and proper time into play, and that is really what we want. Let's see what happens. So both both sides of the equations times gamma u. So on the left side we have the first component, gamma u times f3 times u3 over c. So this equals gamma u times d over dt m0 gamma uc. Okay, and as we know, this equals gamma u equals dt by, or the dt over d tau. We see that the dt's cancel out, and we have just here d over d tau and the expression in brackets. So this equals d over d tau. We already knew that this is e over c, and already now we have truly the first component of what we want to call, define as k0, our first component of our force vector. Now we look at the other components, the other equations, times gamma u times f3. Now the spatial components 1, 2, and 3, and this equals, so we have to do the same game, and we see we get gamma u times d over dt, and just get here also the proper time derivative, but of this expression, 0 gamma u times u1, 2, and 3, and this is equal to the proper time derivative of our four momentum, p1, 2, and 3, and this will be the other three components of our force vector. Okay, this leads us now to the force, or Minkowski force, in the following way. Okay, 0 equals, it's just again a summary, p by dt, p0 equals gamma u 3 times u3 over c, and k1 p1 gamma u f3 1 k2 and this we can combine into one 4-vector. And now we have to check the consistency, if it is really what we need for the connection with the 4 acceleration. Okay. So what we wanted was that k mu equals m0 b mu. And if we compare this to our 4 acceleration vector, so we take now, so our 4 acceleration vector, we see what the components look like, and if we, in case that we now multiply this by m0, we directly see that we get as result k mu, as k mu in K-mu we have also our expression for the three-dimensional relativistic force. Okay, and this all leads us now to the relativistic law of movement. So I call it now the four relativistic law of movement of particles in the four-dimensional flat spacetime of S special relativity. This is following formula K mu equals proper time derivative of for momentum equals gamma u times u3 f3 over c just f3. This equals m0, the rest mass times for acceleration. So let's do an example. We want to construct the right force law for the Lorentz force. Okay, example, we have F3 should be the Lorentz force, that means an electric charge times electric field strength plus velocity u3 cross product magnetic field vector B. So let's construct from this the 4 vector. So we would have proper time derivative P, and this should equal then, now we insert for F3 just this equation here, just this formula for the Lorentz force, and so we get gamma uq times the 4 vector components 1 over c u3 times e. Why just this component? So just because we multiply by u3. So if we multiply this Lorentz force by the velocity u, we get for the expression u3 cross product b times u, we get 0, because this vector here, the vector resulting from u3 cross product b, is perpendicular to the velocity vector itself, and therefore the scalar product equals 0. So it's just have the first component, the electric field strength vector E. Okay, and for the other vector components we get E plus U cross product B. And this will equal rest mass times B mu. And with this we would be able now to calculate the movement of particles in electromagnetic fields. But instead of that, we want to do another example. Now we want to consider a central force, and we will show that a central force in a lab frame S, which is acting upon a particle, we will show that is when it's transformed towards S primes to another inertial frame, we will see that in this other inertial frame it is not acting on the particle like a central force. And this would mean that as a central force in Newtonian physics is conservative, it follows that this is not a property for all inertial frames, and thus it's not Lorentz invariant. Okay, just let us do that. So we have to do mainly few things. First, we need a full force law for a central force, and then we do general Lorentz transformation, and then we will get an expression for the primed inertial frame for this transform force, and we'll see that its form deviates from what we know, from what is needed for a central force. Okay, so second example, a central force. So we know that a central force, call it F3, would equal that the force is just depending on the distance. Let's call it a rated distance r. So we have Fr times the vector r. And yeah, we can further write it like that when we have a unit vector pointing in direction of r. Okay, from this we construct now a 4 force vector. It means kmu, I call it kmu C for central. We get gamma u. Here we just insert for F3 Fr times r times this vector times u divided by c, and here we have now we do what we said we will do now, a general Lorentz transformation, general LT with velocity v. Okay, if we do that, so now I will really abbreviate all the calculation and just show you the this leads to a lot of calculation, and this leads to the result the following way. So f primed, I just go for the spatial time of the spatial part of the 4 vector. So f primed 3 equals f3 of r divided by gamma v, 1 minus v times u over c squared times r prime plus gamma v gamma u c d tau v. So, and here we can see that f3 is not just a function of r primes, but also a function of the second expression here after the plus sign. And this means that f primes is not a central force. So f primes f prime is not a central force and therefore not conservative.